All right, so for this example, we're going to take f of x equals 2 to the power x, and we're going to use that and find the linearization of that function at x equals 3. Just as a reminder, let's write the L of x equals f of c plus f prime of c times x minus c. This is what is the function value at c, and then plus the slope of the tangent line times the change in x, which is x minus c. Okay, that's the basic idea of a tangent line equation, and that's what linearization is. So, first of all, the point in question, the point of tangency, can be found. That's going to be x equals 3, comma, and then f of the y-coordinate will be given by f of 3, which in this case is going to be 2 to the power 3. So that's equal to 3 comma 8. Okay, so that's the point that we're going to be working with, the point of tangency. And now the slope of the tangent line, so slope of tangent line, is going to be given by f prime of 3. So now what's f prime? F prime is, so if f is 2 to the x, then I'll write it kind of small here. F prime is a single prime of x is going to be 2 to the x times the natural log of 2. We learned that back in chapter 3. So this is going to be 2 to the power 3 times the natural log of 2, which would be 8 natural log of 2. And I'm just going to leave it in that form. That's an exact form. If you multiply 8 times the natural log of 2 and evaluate that with a calculator, then you'll get, a decimal approximation of this irrational number. So you can get that if you want. But I'm just going to use that. So let's see. Now, the linearization that I'm looking for comes from the equation of the tangent line. It's going to be L of x equals f of c, which is, remember, the y-coordinate at this point, so that's 8, plus the slope we found, 8 natural log of 2, times x minus the c value, the x-coordinate of the point of tangency, which is 3. That was specified, in advance. So there we go. So there's our linearization. Now, the linear approximation we get from that is we're going to say that the function values, 2 to the x, is going to be approximately equal to 8 plus 8 natural log of 2 times x minus 3. Now, why would you want to use this linear approximation over the original function? The original function is obviously way simpler to write down and easier to evaluate. Well, it's easier to evaluate for a human. But actually, this linear approximation, it's right in the name, it's linear, okay? This is a linear function. You could simplify this to just y equals mx plus b. And it turns out linear functions are easier to work with in general, right? Like you'd rather have a linear function than an exponential function. And in particular, for like computers, to evaluate a linear function is easy, whereas to evaluate or just work with an exponential function is more difficult. If you're programming a computer to solve a linear equation, that's easy. If you program a computer to solve an exponential equation, that's a little more difficult. And it takes more memory and more time. So linear approximations are valuable in applications because they can turn complicated, difficult functions like exponential functions or trigonometric functions or log functions, they just turn those into linear functions, which are super easy, at the expense of some degree of accuracy, right? And then you can do an analysis of how accurate you're going to be on your interval that you care about to determine whether it's worth it to do that substitution. Okay, so let's check. If we are, let's say we're going to look at, let's say we have x equals 3.1. Okay, let's take an x value very close to our point of tangency, and let's take, at that value, let's see what the error is going to be. Well, if we do f of 3.1, this is the actual function value, it's going to be 2 to the power 3.1, and I did this in my calculator earlier and got 8.57. So that's our actual function value, approximated to 2 decimal places, okay, approximately. And then the value of our linearization, L of 3.1, that's going to be 8 plus 8 natural log of 2 times 3.1 minus 3. And that turns out to be 8.55 approximately again. So for an x value just 1/10 of a unit away from our point of tangency, we see here that the error is the difference in values. The error is going to be like the, how would you put this? It's the actual function value, f of 3.1, minus the value of the linearization. So it's the difference between these, which, by the way, is what this purple line was indicating. It's like the horizontal difference, like how far apart are they, are the outputs. That's the error, and that's equal to, in this case, just 0.02. So that's pretty small. Pretty small. So that means it's a pretty good approximation, at least when you're only 1/10 of a unit away from x. If you pick like x equals 5, which is pretty far away from 3, then this approximation is going to be nowhere near that good. The error is going to be much bigger.